Merry Christmas and welcome to Academic Digest class. So this question says, mention 4 types of motion. So the first one is what we call linear motion or rectilinear motion, or you call it translational motion. Rectilinear motion. Rectilinear motion. Circular or rotational motion. Another type is what we call periodic motion, where you find things like simple harmonic motion. Then we have random motion. We have so many of them. So there you have it. So the next question says, a body starts from rest. Okay? Then as this body starts from rest, the body starts, moving. It starts as rest, then starts moving with acceleration. I told you, once you see acceleration, just think of it that you are going to be using equation of motion. So then they say covers the distance of 25 meters. Calculate the time required for it to cover the distance. So the equation we use for this is 50. This is question 52. So we'll say starts from rest, U equals to 0. A equals to 0.5 meter per second square. Then S equals to 25 meters. Then we don't know T. They're asking us to find T. So to do this question, all just this to say S equals to UT plus half AT squared. U is 0. 0 times T here, everything will be 0. So we're just going to be using S equals to half AT squared as our equation. So S is equals to half 0.5 T squared. And S itself is given to us as 25. So if we do it very well, we see that this is going to give us 0.25 T squared equals to 25. Then we now get that T squared is equals to 100. So take the square root of both sides. So T will be equals to 10 seconds. That's our final answer. So let's move to question 53. So question 53 says, an object is rotating about an axis O, and that O means that it's rotating at the origin. And for example, if we say a stationary body, or you say a body starts from rest, we are talking about its beginning point. So if it's rotating about that origin, it means that initial velocity is 0. In fact, even if you are not given initial velocity, once you are told that there is acceleration in a circular motion, in most cases they don't always give you the initial velocity. So reading this question, when you finish reading it, you now join us. So we'll bring out all the things we are given. We are given R to be 0.45. We're given R to be 0.45. Yes, we're given R to be 0.45 meter. We are given acceleration alpha to be 4.2 rats per second square. Then we are given T to be equals to 3 seconds. Then they're asking us to find velocity, the angular speed. So initial velocity will be 0. So we'll simply use W equals to W naught plus alpha T. And when you do the mathematics, you get that W is equals to 0 plus 4.2 into 3. W will be equals to 12 rats second. So it's going to be 12.6, sorry. 0.6 rats, 12.6 rats. So 12.6 rat per second. Alright, let's move to the next one. So there you have it for question 53. We are moving to question 54. So for question 54, they said, given the following. Okay, given the following. So there you have it. We tried to look at that question. So we now analyzed it and we got that. See what we did. We said from force equals to G m1 m2 over r squared. That is Isaac Newton's. We now say we have F to be equals to mg. That is, since on the surface of Earth the force acting will be equals to, that is the weight, that is that mass and what is pushing it down. So when we did it, after doing everything, we got mg to be equals to gm. So cancel. Then we try to make m subject of the formula. And when we made m subject of the formula, we substituted the given values. And then after doing it, we got this. So copy and paste. Let's move to the next one. Let's move to the next question. The next question says, define gravitational potential energy. The next question says, define gravitational potential. Sorry, not potential energy. There is difference between the two. I think that's why I even said I would talk about this. When you hear potential energy, it talks about energy possessed by a body due to its mass. But when you hear gravitational potential, think of it as its velocity at different positions under the Earth's surface. So we normally check it in three places. When it is at the Earth's surface center, that is a distance from the center. When it's at the Earth's surface, and then we check the strengths. So see how I analyzed it here. So you can copy it from here. I did a lot of work on it, so to save time. So I said the gravitational potential inside the Earth varies depending on the distance from the center. And I said for better understanding, but it means like to ease the understanding, we apply the following concepts. Gravitational potential at a distance r from the center of a mass. So that is gravitational potential. That is, see, for example, let's say I have this now. So I'm now saying gravitational potential at a distance r, so from here, from the center of mass. So let's say it's not must that center of mass is at the center, it can be at any point. So from the center of mass, so gravitational potential when it's here. Then we have another case that we will consider. When this gravitational potential is right here, which is the second case, we'll consider it with r. So, and I said, and whenever it is r, gravitational potential at r is constant. It is always constant. Why? When it's here, when it's at a distance from the center, we use an equation to learn it. So we say that it is given by, that is, the gravitational potential at the distance from the center of mass is given by the formula Gm all over r. Notice that everything you see here is the same thing as that Newton's equation. Just that in this case, you've already cancelled, you've already done this. What you did here, remember, you've already done this, so that at the end of the day now, what you just have is this time around is G and M. See, G and M. It's just like C. That time that we were here, that we did M. So when you consider the force on Earth, which is mg, then consider this. Notice that this G that you see here is the gravitational potential. So this is gravitational potential from distance, or from distance at a distance from the center. This is the formula. So this is how you get the formula, which I said is GM over R. Now somebody wants to ask me, what is not R square? Yes, so we are just considering one distance. We are just considering a distance from the earth. That is why we are using this. Not like maybe we are considering the whole earth. So from a distance, center of a mass is given by. So then the negative sign that you're seeing here is simply showing you that whenever something is acting on the center of earth, it's acting downwards vertically. I've explained this in class before. So it's in negative. We normally say that gravitational potential of the earth is negative because it's acting downwards, and you know that in the y-axis, upward means plus, downwards means negative. So we now said another concept is gravitational potential inside the earth. So I now say for uniform spherical shell like Earth, the gravitational potential is constant. You need to know that it's constant. Now I now said note, gravitational potential at a distance r from the center of Earth, where r is less than r, with r being the radius of the Earth, can be expressed thus. So Vr equals to, so Vr, that is gravitational potential from a distance from center distance, is equals to gravitational potential of the surface of Earth minus Gm over r, that is radius at the center, then plus Gm over r cube, then multiplied by r square all over 2. This is a formula, very important formula. And I say where V into r is the potential at the surface of the Earth. I'm always putting r close to it, so you know the difference between when it's at the center of the Earth and when it's the distance from the center of Earth. Now I now said another concept you need to know, which is the third one, is what we call gravitational field strength. Gravitational field strength. And I said inside a uniform sphere, the gravitational field strength decreases linearly with distance from the center given by Gr, that is from the center, potential from the center from a distance, potential at a distance from the center is equals to Gm then r all over r square, where m is the mass enclosed within the radius r. Alright, and I said key points, so more like a takeaway. Key points: at the center of the Earth, the gravitational potential is at its minimum, most negative value. The potential is highest, least negative at the Earth's surface. Okay, then the gravitational potential increases as you move from the center to the surface. So then I said note, the gravitational potential inside the Earth is a function of the distance from the center and can be calculated using the above listed formulas. So thank you very much. Take your time and think about it. Alright, let's say calculate the tensile stress in a copper wire of diameter 2.0 cm when it lifts a load of 1000 kg. So tensile stress, you know that stress is more like pressure. So this is where we solved it. So first of all, analyze everything we are given. They gave us the diameter, and diameter is 2r, which means that r should be equals to diameter over 2. So, and that is 2 cm. To meter is going to be 0.02. When you divide it, is 0.01 meter. The mass is 1000 kg. Formula for stress is force over area. Area of wire is given by pi r square. So if you do 22 over 7, then times r, which is 0.01 meter square. So by the time you do it, you get 0.00311429. So F is mg when lifted. Like when you're talking about lifting something or something going up and down, F is no longer me but mg. So stress is going to be equals to 1000 times minus 9.8 because it's going up. Some textbooks will ignore the minus. There is no problem if you choose not to put the minus, but I'm putting the minus to show you that it's going up. That's what it means. It's not like maybe the value is negative or whatever. But what it's showing you is that the body is going up. That's why I put down negative. So by the time you do the maths divided by, you are getting 31 in million, 181 in thousand, then 393, then Newton meter square. Sorry, yes, it's supposed to be Newton per meter square. Yes. Alright, so let's move to the next question. I say, what is scalar product of two vectors? I explained it here. That is 57. Scalar product, also known as dot product, is given by A dot B equals to magnitude of A magnitude of B cos theta. It is a scalar quantity. So it simply means that scalar product talks about magnitude of a particular variable. It can be anything, but here I'm using A and B. Then and the cosine angle between them. So I now said it's a scalar quantity as I dot I, J dot J, K dot K, its direction product results to unity. Whenever they tell unity, it means that it results to 1. Alright, next one. That is question what now? Question 58. A body of weight 50,000 Newton falls freely through a height of 1,500 meters. What is the work done? Okay. So weight is 50,000. Height is 15 meters. So work done is going to be weight times height. And you know that weight is mg. So it's the same thing as saying force times height. This is work done on a force field, gravitational field. Thus, weight equals to mg. Work done equals to 50,000. That is the weight times 15, which is giving you 75 million joules. That is the work done. So for 59, they said 1,500 joules of work done is in raising a block from the ground state to a height of 12 meters. It's done in raising. Calculate the force on the block. 59. So this is how we solved it here. I said W is equals to mgh, and that mg alone is equals to force there times the h. So mg, put it together as force. So to find the force now, you divide both sides by the height, which is 12. So you get F equals to 125. So you can still put this to be negative 125, being that you can put it to be negative, being that the g that is inside this force is going to the same thing as, since it's raising up, it's going to be a negative 1. But in most textbooks they don't put it, but that sign shows that it's lifting up they are talking about. If it's positive, it means that it's bringing that, but most times they ignore it. Now question 60 and the last one for this video, it says the mathematical expression for work energy equation is. So whenever they ask you mathematical expression for work energy expression, or they ask you work energy, it simply means work energy is telling you that work is equals to kinetic energy. So I did it here. I said that work is equals to change in kinetic energy, or you can say that work is equals to kinetic energy. So the mathematical expression is simply Kf, final kinetic energy minus initial kinetic energy. Then we proved it, how we got it. We said going to kinematics, we know that distance is equals to ut plus half at squared. At initial velocity, u is 0 times this, everything here is 0. So half at squared. Remember that a is equals to velocity, change in velocity, or derivative of velocity over time. So when you put this t squared, you see that t squared will cancel this t. You have vt. Now S is equals to Vt. So remember that work is equals to MAS. Now replace V over T for A. Now when you do S, which is Vt that you got here, put it here, then you see that V over T times Vt, T and T will cancel out. Now V times V is V squared, then M. Now remember that there is half here that will carry it here. There's half in this thing. Bring this half down. So which means that initially this was half Vt. So by the time you do V times V, you then get V squared. Then bring that to your half. Let me put the half here. half here, and we know that kinetic energy is equals to half mv squared. So you've proved it is equals to kinetic energy. Thank you. If you don't understand, take time and play the video. These are not meant to be understood once. You play it over and over with silence, go through the difficulty, then you get it. Thank you. Subscribe to my channel.